From the beautiful studios of Way Happy, this is Mr. Meyer and 11 for compound events. Now, these are events that you have to worry about, like, do they share some stuff in common or don't they? So let's get started with mutually exclusive. Now, the first thing you want to know about mutually exclusive is that the two events can't be in the same kind of bubble sort of thing. Think of it as if I want to interview all, I want to randomly, sorry, not interview. I randomly want to pick a student, and it's either a sophomore or a junior. Is there anybody that could be in both of those bubbles? No, you're either a sophomore or you're a junior, right? It's not like you can fit in there. So you would be called, those groups would be called mutually exclusive. Sophomores and juniors are called mutually exclusive because you're not in both of those groups. Um, if you're in band or you're not in band, those are mutually exclusive groups because you're either in it or you're not. You're not kind of in it. No, you're in band or you're not. So this mutually exclusive means that you are two separate groups, and so if they are, that's called mutually exclusive. All right, so look at example one. We have students donating blood at a blood drive, and there's a 9/20th probability of having type O, and there's a 2/5 probability of having type A. Explain why that type O and type A are mutually exclusive. Well, can you have the two types? No, you have one blood type, right? So you are either one or the other. You have just one blood type. And thus, that's why they are mutually exclusive. So, boom. All right. What is the probability that they have type O or type A? Well, that's like you kind of see over here, but this is how we write it and everything. So you might want to take a look at that. But the word or means add the probabilities together. So I'm going to do the probability of O or, so added to the probability of A. So I'm just going to take the stuff from the information up here. Type O, you had a 9/20th chance. Type A, you had a 2/5 chance. And I'm just going to add those together. So common denominator, 9/20. I got to multiply that one by 4. So 8/20 was that 17/20. That is the chance that you would have either type A or type O. So if we grab 20 people, we could assume that about 17 of them will have type A or type O blood. So there you have it. That is mutually exclusive events. So what about inclusive events? Inclusive events a little tougher. Groups that are the same, like not juniors and sophomores anymore, but how about juniors who are in band, or juniors or band members? So you could be a junior, you could be a band member, or you could be a junior who's in band. So you would be in both groups. That's what an inclusive group is, something where you could fit in both bubbles, or there could be people in both bubbles, or there could be outcomes in both bubbles. Those are called inclusive. And again, look here at this formula. You will see that an inclusive event, again, you just add it together, but you have to watch out. You've counted people twice. You've counted the person who's in band, and then you've counted him again as a sophomore or whatever I said. And so therefore, you've counted that person twice. So make sure you subtract out anyone who you counted twice. In other words, who was in the middle of both of those things. Make sure you cross them back out because you should only count them once. A lot of people like to use Venn diagrams for this. I'm a big fan of Venn diagrams. But here we go. We'll use the formula. So find the probability of a number cube of rolling a 4 or an even number. So you're like, oh, okay. If I roll a 4, that's 1/6. If I roll an even, that's 2/4. So that's 3/6. But wait, 2/4 is also a 4. So I counted the 4 twice. So I need to subtract off the 4, which was in both groups. So I subtract them out, and now life is good. So there you go. You should have your answers 3/6 or 1/2. There is your probability of rolling either a 4 or an even number. What about rolling an odd or a number greater than 2? So I'll be like, all right, rolling an odd, you have a 50-50 chance, or 3/6. Rolling in a number greater than 2, that's what? 3, 4, 5, 6. That's 4/6. So right now the probability is 7/6, which doesn't make sense because that's bigger than 1. So something's wrong. Oh, wait. We counted an odd numbers in the numbers that are greater than 2. We said it was 3, 4, right? I said greater than 2 is 3, 4, 5, 6. I counted this guy and this guy twice because they were also odd. So let's subtract out the 2 6 that we counted twice. And so what do we have? We got 3 plus 4 is 7, minus 2 is 5. You got a 5/6 chance that if you roll a dice, it'll either be odd or a number greater than 2, which makes sense because the only one that doesn't work is the 1, right? Or I'm sorry, is the 2 because it's not greater than 2. Beautiful. All right, let me ask you a question and I'll be right back. All right, nice work. Now let's go on to example 3. Now here's the problem. You got 1,560 students that are surveyed. They're juniors and seniors, and this 840 were seniors and 630 read the paper. Of that, only 250 of the ones that read the paper were juniors. What's the probability that they're either a senior or they read the daily paper? Well, first I'd be like, oh, okay. The chance that you are a senior is 840 out of 1560. And the chance that you read the paper is 630 over 1560. And all I'm going to do is add those together. But, excuse me. But there's a chance we called some people out, that we counted people twice. So that's where you got like this group of seniors, right? This is the seniors, and we know that there's 840 of them. And then here's the people that read the paper, and we know that there are 630 of them. But now I know that of the 630, some are seniors, some are juniors. And in fact, I know that only 250 are actually juniors, or 15. So 215 should be here, which means 415 were seniors, right? Because notice that the paper readers still add up. This still adds up to the 630 that we had. So there's still 630 people in the paper bubble, even though I crossed them out 630. 215 were juniors, 415 were seniors. If you want, you could clean up your senior bubble now. This looks like there's 1,200 seniors, and we know that's not true. There's only 840. So maybe you want to subtract 415 from that and get 425 to just get all your numbers right. So now there's 425 people that are seniors who don't read the paper. There's 450 seniors that read the paper, and there's 215 juniors that read the paper. And so there is our little bubbles. And so what do we do when we do this problem? We're like, oh wow, look, there is a group of kids. In fact, there's 415 kids that I did not want to count because I counted them twice. So there is my final answer. Was that 1,400 minus 4? It's like 1,000, or what would it be? 840 plus 215 is 1,055. So there's 1,055 kids who are either seniors or read the paper out of the 1,560. And so there is my probability. If you want the actual probability or the decimal, or you want to go calculator, go ahead. If I take my calculator and I type it in, you can see that it's about a 67.7%, sorry, 0.6%. Or math, change the fraction. I like 211 out of 312. So 211 out of 312 chance that you will have somebody who read the paper or is a senior. All right, last one. Let's talk about this. You have these kids that are doing a report on butterflies, and there's 8 different types of butterflies. What's the probability that 2 kids pick the same? At least 2. So that means 2 kids could pick the same, or 3 kids could pick the same, or 4 kids, or 5 kids. Oh my gosh, we have to do so many probabilities and add them together. That's pretty tough. I wonder if there's a better way. And oh wait, there is probably, right? Well, let's see. If at least 2 kids, then what if they all picked different ones? That's the only group that we're not talking about, right? So if they all pick a different one, that's like the complement. Yeah, that's the complement. So let's see what the chances are what's the probability that they all pick different, right? So if they all pick different, and then we'll just do the complement of that because that's way easier to figure out. So the fact that they all pick different is, well, there's 8 types. And so now I got to figure out, all right, the first kid, he's got 8 to choose from, and there's 8 total. And then the second kid's got to pick a different one. So there's 7 out of 8. And then the third kid's he's got 2 already chosen, so 6 out of 8. And how many are we doing? 6 kids. So there's only 3 kids. The next kid's got 5 out of 8, and then 4 out of 8, and then 3 out of 8. that would multiply all that together. That's the chances that they all pick different. By the way, that could be done also with a permutation. You can see that this is 8p6. That will get you choose 6 out of 8. Order matters. That makes it a permutation so that they can't have different combinations. And on the bottom, that's 8 over 6. So I could see what this is on a calculator. I go 8 math p6 divided by 8 to the 6th power. Yuck. So there's about a 7% chance that they would all pick different, which means there's probably a 93% chance they're going to, at least 2 people are going to pick the same, right? Because that's at least 2 people or 3 people or 4 people or whatever. And so it's just the only thing that they're not all different. So I'm going to do 1 minus the answer. And then there you have it. You have a 92 point, I didn't pay attention to the decimal, 301. 92.30, was it 1 or 9? 9 percent chance that they would pick at least 2 the same, because that would mean that they didn't all pick different. All right, that's it. You have a great day. Stay happy, and I'll see you tomorrow.